Good afternoon. It's Sunday, the 25th of June, 2023, Seattle, Washington. A warm afternoon. Reading about the arithmetic mean and the geometric mean and the harmonic mean, the idea is to figure out how they're the same or how they're different, and what conditions they are actually the same, and when in the extremes they're the most different. I was reading a little bit about it, and from what I understand, there's the arithmetic mean and the harmonic mean, and between them is the geometric mean. And then otherwise, the descriptions of what goes into things are things like about the root mean square, which is taking the mean of the product of the squares and taking the root of that, and this kind of thing. So I was learning a little bit more that how that's kind of how it's done, that's computed for terms in powers and so on in electrical circuitry and this and that. And how it so relates to things like sum of squares, these products of squares, about then what they are intended to detail, and things like counting arguments in the discrete, and otherwise when there are these continuous and discrete systems, is about for geometry's sake largely, but also probability's sake. And then trying to figure out how the event of sampling and this kind of stuff is essentially is as stochastic is in the space of events that are discrete, whereas the real world and the actual support space of all events is continuous. These are the kinds of things that go into the thinking to help explain why, in the overall science of things, that beneath logic and mathematics, which is where things are deterministic and causal, is discussed the Platonic realm and this and that of the mathematical universe. Then there's the stochastic realm, and so science and all such matters of inference from events in the sensory and the phenomenal, in the phenomena, is so made that the theory of the philosophy of science is about the same as the theory of the philosophy of statistics. That there's no establishing something as true or according to science, only that according to a given theory it's not false. It's called falsifiability. And so the theory of science has come a long way, and you can point at Roger Bacon, or you can talk about the Enlightenment thinkers and all this kind of stuff that came about the industrial age and its relevance after what was the empirical, which is where the empirical formulas reigned, and to getting to where this scientific and statistically validated experiments in science and statistics instead came to reign and govern the systematics of the axiomatics of the theories that so follow that they're strikingly successful. And so the scientific method and its falsifiability, after somebody like Karl Popper or somebody like that in the 20th century, finally kind of put the last bolt in that basic notion with regards to causality and correlation, then has that statistics is much the same thing. There's not so much validating a statistical hypothesis as not invalidating it. So it's to be understood that according to the theory of science and the theory of philosophy, that they're much the same thing. So when there's one overall theory of everything, and this theory of everything, that it is a science and it is a probability theory or statistics says about it. And so that just kind of essentially reflects on whether there's uncertainty or chance. So there was these notions of nothing and being, these complementary notions of the universal and void that are the primary objects, one or the other at any given time. One or the other on any given consideration is a primary object, but that it vacillates and that it's constantly changing reflects that what is really arrived at as true has to affect that it's resistant to meddling, that otherwise it will constantly reinforce itself, this theory, these objects in their theory, and all the related theorems and all the structures of structuralism and constructivism that would exist in it. For that, if they didn't, they wouldn't. De facto, they do. In a usual sense has been discussed here about the justification of axiomless natural deduction and its strength and its centrality and its primality, ... So, anyways, then figuring out that then that the science and and the statistical efforts that so follow, but science is attached with this, central to it, part of simply our observer framework, that that we are objective observers each other and subjective observers each other with regards to the interplay of objectivity and subjectivity, that the science is a well-founded philosophy, and so it kind of, again, that it stands for itself in terms of its validity, makes it so that that's why everybody has kind of the same theory. I was thinking about this the other day, and I thought it was amusing because there's a regular quote, something like, "Great minds think alike." And then the idea is, well, the greatest minds think the same. And then finally, like, a greater mind thinks this, that something's greater than us. But at the same time, whereas anyone is indeed encouraged to maintain their entire framework of all such abstract, paradoxical, fantastical, absurd notions, ideas, theories, they all live in the abstract as conjectures and in the world of theory, in the realm of consideration, the realm of free thought. And everybody's different, largely. But then that there's this common interface, this shared medium for everybody, is the usual hallmark of what is called Platonism, which though is fractured in many different cults and tempered ideologies or estrangements. But Platonism, that then there's strong mathematical Platonism, as was discussed, that Gödel, who's considered a great thinker, adhered to, found that we only discover these truths, can't invent them. Truth is discovered, lies are invented. When a lie is discovered, that's a truth. These kinds of things. Make for that in this way. The scientific method is a common fixture, and is part of the theory. And it thus arrives at that then logical systems, as they become more complete and rich and engaged in natural language and engaged in matters of worldly fact, arrive at why they basically become implemented as experiments, as scientifically oriented, statistically oriented. That basically, along with the deterministic data structures, come a bucket of statistics that's about the same size and space, and that for any given application algorithm, they get processed with about the same resources of constant time processing, half and half, as it were, to figure out what's the meeting in the middle of those between statistical inference and maintaining means, medians, and modes, and other characteristics or sample statistics, and what are called the summary statistics, whereas an average is a great summary statistic. That the notion of the maintenance of these summary statistics in the summary that goes along with the state of data structure and algorithms is a large part of what's called something like adaptive algorithms, adaptive containers. That there's this algorithms and data structures are defined for computer programming, and the implementations in software engineering are logically, then concretely in the machines. Von Neumann architecture, Harvard architecture, ... Harvard architecture, these VStack machines, or any kind of machine, in terms of their asymptotic runtime with an unknown distribution of their inputs. So their inputs support a space. It's called a formal language, which is basically given words, given size, alphabet, and length, and occurrence or frequency of words. Those are the inputs. And it's often called that the size of each of these inputs is called n, on the order of n. And so the big O notation and theta notation and asymptotics and all this in the analysis algorithms and data structures is according to the time and space terms as so follow according to the law of large numbers. That is an unknown distribution is so what will arrive, so it's basically is indistinguishable from a uniform distribution of these elements as so arise. So all the standard libraries provide adapters to adapters. They provide implementations of these usual regular data structures like so. So then the very idea is that if the more you know the distribution of the input, the more there can be perfectly tuned, optimized, adapted an algorithm to both establish and maintain the data structure and to service its operations. This is where usually the operations of a data structure are defined in terms of what it costs to service the operations after the data structure is constructed. They don't often necessarily always include the maintenance of the data structure. And so when that's like insertions and deletions or reorderings and sortings after something like that is so. For data structures that depend on such notions vis-a-vis data structures that depend on a tag or a code or a hash or a signature or their input and datum with which are associated that are stored otherwise, and usually the either the bitmap or the binary tree. So that is just kind of gets into then that for these summary statistics, the idea is that there's a notion that there's basically a formal approach to prove, to show, to demonstrate that there's a certain variety of ways to keep summary statistics that go along with any access to a data structure, which will result that then over time that becomes a sensible, fungible, and tractable elementary object in itself for the input and the process and the output, as it were. Something along the lines of the expected costs as it would be to maintain it or to recreate it or to reorganize the data structure, what results and arrives at that given perfect information about a distribution, it's possible to implement a perfect or optimized implementation of an algorithm as about its data structures. And so then the adaptive is these data structures that change over time, their organizations and access and their patternry and their backing in accords with what kinds of distributions are essentially in effect under a workload, under units of work, or what become in the message passing infrastructure, or in streams, or in batches, or in buckets, message-oriented inputs and outputs, requests, responses. This is just kind of the area of the modern distributed systems programming, or corp software ang, enterprise corp software ang. That's just kind of the perspective of distributed systems and message passing, request responses, and units of work and business objects and this kind of thing. But the reflection on the fact that the summary statistics and what they are and how to gather them and which ones and how to implement strategies to truncate them or to refine them and how to maintain reserve values and this and that, or how to how much of a mode to keep and how much of the median to track, and how to break that down into buckets so that over time such things can live and grow over time without running away or running down vis-a-vis the usual maintenance-free considerations of the generic data structure of the usual standard definitions and their asymptotic runtimes and their asymptotic space terms. That the point is that there's a setting, kind of like when you look at Huffman codes and given an alphabet and knowing the frequency of the occurrence of its terms, that you give the most frequently occurring terms the shortest codes, and that's what implements compression, entropy coding, vis-a-vis arithmetic coding, and that is alphabet coding. and also it's sort of run length encoding. The compression is implemented this way, and it's provable that it's optimum. It's a well-known fact in computer science and compression and entropy coding. So then the idea for these adaptive data structures is it's not so different for what summary statistics are generated off the mean, median, mode, or these various notions of min-max and counts, histograms, and other summary statistics. And then figuring how those are limited, that they basically fit in a fixed width box to go along with the fixed width box or block allocated to the data structure and the algorithm for its maintenance and operation and access and behavior. That I don't know anybody who's really kind of put that out there as what would be something like everybody should know this because it's mathematically so that this is the best way to accomplish things. But in the world of what's called intelligent or adaptive containers and distributed algorithms and this kind of thing, it's a usual closely held approach to things that would otherwise be intractable, but given the use of information, are simple. So going back to the arithmetic and harmonic means, then the idea is to follow up from Kazarinoff and see what he says later in this book. So we got up to defining greater than, and the properties that it maintains in terms of relation, in terms of its elements in each other. And then before we talked about one of these things is not like the other, and equals and not equals, and tautologies. And when you think about tautologies is when they're the most same or the least different. You can see that those would be complementary duals, whether the most same or the least different, to define things in terms of same and different, to define things in terms of equals and not equals, to define things in terms of coming together or coming apart. That all these kinds of tendencies and propensities build into the framework what are things that otherwise in the discrete and in digital and scalar and values are equals or not equals. And in the scalar are greater than or less than. In the trichotomy, they're real numbers or scalars. Then there's discussed the idea of the scalars and the relevance of operator calculus to these iterations in scalars. Increment and addition as a pair of these, multiplication and powers as a pair of these, and exponents and tetrads or tetration as a pair of these. What does that mean? It's like, well, when you think about the scale and that those kind of define the scales, and for example, from computer science, you should be familiar that linear and polynomial are on the order square, or exponential are these three big ranges. And in the asymptotics, they define basically one line is, and all the things that are approximately on the order of it are in the space of the exponential, and another one is on the space of the square, or any finite power linearly in those powers. And then there's the linear, which is just on the order of n, that's constant under the term. So then that's where the term or the input size is expected to go to infinity, and then that basically all the lines that are exponentials meet at infinity, and all the lines that are polynomials or powers meet at infinity, and all the lines that are linear meet at infinity, and then that's just pulled back and written as o n squared o to the n. And so in the scale of these things is the idea then to put that in this identity dimension quadrant box. What does that mean? Well, you take the xy plane and you can consider each quadrant, and then you just make each one a box, and the corners are 0, 0, and infinity, infinity. And so then if you think in terms of what that means when that shrinks down to 0 is what that means. So one way to think about that, there's a fellow, his name is Bois-Reymond. And so he was in the era of Veronese Gestalts and the 1900s, the 18th century. or I'm not exactly sure the timeline on that. Anyway, he ended up talking about the infinite Tarkal call, and he talked about all the real functions. And then you can order all the real functions basically algebraically by making an ordering of them, just like we've been talking about the order of the real numbers and their trichotomy and this and that kind of stuff. You can talk about the order of these functions, and that there are more of them than there are real numbers, because all the expressions in real number variables are real valued formula. Maybe not all of them. I'd have to think about that in terms of the complex. If they're taking the roots of complex numbers, but in the positive quadrant, they are, which is nice. And according to the identity dimension, they are. So they all fit on this long line. So that's called the long line. There's another another name. There's a collision in the definitional dynamics of the thing. And then when they talk about integers and the hyperintegers, well, what's the hyperintegers? It's like, well, it's kind of like going to infinity and then going out with ordinals that all the way to some higher transfinity. It's like, whoa, is that applied? And it's like, no, it's just kind of a thing posited to exist, and it's about the descriptive terms of the space of the words and the ordinals, and so it's kind of detached from geometry. Oh, so they call it the long line? It's like, yeah, well, actually, the long line is this long line of Bois-Reymond, and it was first, and it's a linear curriculum, and it's where the space of real functions sits on it. So for line continuity, field continuity, and signal continuity, then they all kind of connect about this long line continuity. So geometric, arithmetic, and geometric means. Theorem. So he starts using some computations and some exercises, and he talks about the fundamental theorems. A slightly more sophisticated mode, he describes the geometric series: 1 plus 1 over root 2 plus 1 over root 3 plus ... plus 1 over root 9999 plus 1 over 100, which is just root 10,000. And he says, how big is it? We might find it difficult to make an accurate guess. If we had a computing machine in enough time, we could make a computation of this number accurate. However, inequalities will help us to make a good estimate in a much shorter time. So then he provides this formula: 2 times root n plus 1 minus 2 times root n is less than 1 over root n is less than 2 times root n minus 2 times root n minus 1. He says it's not difficult in our experiments, and he describes that working out, he starts describing some of the process of working out formulas and trying to derive how it can be shown that they bracket out and bracket down, and it can be manipulated and expressed in each of the particular steps, showing all that the derivational terms and the quantities are kept along. Experimentation is a typical occupation of mathematicians. We conduct many experiments. Only our experiments are made with numbers, geometrical figures, and various other abstract objects. And so in this sense, this isn't so much about the scientific experiments, but it is in kind of the action of it. It's as much the ansatz, each of the setups, trying combinations, trial and error. With regards to that, after the experiment's done, then it's a mathematical effect that's enduring, and then with the idea that it has a foundation and it's held up all together, and the definitions are sound and valid, and the axiom's not false, then it ends up being a mathematical fact, a demonstration of mathematics, or a theorem that's enduring. Our experiments, like those of natural scientists, are mostly failures. I'm not so sure about that, because in the mathematical space there's is it a failure if it's wrong? Yes and no, because it's just not a thing. It's just like it's considered a different class of things. There is only do or not do. That is one way to look at it. But here he's trying to encourage people to expect that it's kind of like writing programs. And as you write programs and confront issues and syntax and correctness and well-formedness and design and analysis and the operation of the algorithms and with regards to unknowns and this kind of stuff, it's called the situation between the keyboard and the chair, because the keyboard is still the usual input device for source code. And tools and tooling vary in terms of what provide for the body of source code, well-defined behavior and expected operation. So anyways, it takes a lot of head banging one's heads upon the desk, or face palming, typical signs of desperation, frustration, and finally an exasperation, and finally appreciation that something was done, or why didn't I think of that before, and this kind of thing. That it's an effort in itself. And so is it a failure, or if it's just a waste? Whether it's the effort itself became part of the context and surrounds altogether, is just the way it was. It's kind of like when people say, well, no regrets. It's like, what do you mean no regrets? It's like, well, don't dwell on your failures. Don't be self-critical. You still have to be self-critical, and when you make a mistake, you have to cross it out and leave it there as evidence of mistake, not erase it. It's not like that. But it does mean as well that it's the learning process is not a mistake and it's not an error, though it can be a waste of hot air. And in a sense here, for example, is that I don't already have a proof for this theorem, so I'm kind of putting off the fact that I don't, because I'd rather just kind of demonstrate how easy it is to have utter facility with the algebraic manipulation of variables and all those techniques. So it's techniques, and it's a grab bag and a toolkit of techniques, and that's about the sensibility and the fungibility, and then for the tractability that so follows in the usual general course of finding what all possible derivations and results live on all these mathematical objects, that then they become facts, and they're simple to understand and relay. And they're enduring mathematical objects, proofs, structures, models, that will be there when you get back. Not going anywhere, but you can bring them with you. Experiments. Occasionally they're successful and we discover a theorem. Then it often happens that more work we have come to believe is true. Then it often happens that more work is needed to give a rigorous proof of the conjectured theorem. Well, here what he meant was he found a conjecture until there's a proof, and it's closed deductively both ways and under any alternatives, not just this is what will see it unfalsified and not invalidated, that it also comes back in the closure and the collective, that it's true forever, and that it's under any alternatives, that the notion of the constructivist is that it can't just be via proof by contradiction, it has to be declarative, and that it has to be definitive, and this kind of thing. Now, that said, I'm not too much quibbling about the difference between conjecture and theorem, but it's more of a putative theorem, where it's not yet validated, but then when it's actually to have a proof, and that the proof would be sound and valid and complete, and not admit otherwise what would be unknowns, is that extra part of it. So all our mathematical objects live in the universe of mathematical objects, but any one is free to define whatever axioms they want on a finite and objective model of any mathematical objects, and that is true. It's not necessarily complete. And those are theorems about those objects, in that theory about those objects. Not necessarily complete. It's at best consistent, and it better be consistent or it's unsound, is how these things go. Then it often happens that more work is needed to give a rigorous proof of the conjectured theorem, which we have come to believe is true by experiment. There's this thing called the law of small numbers, and it basically means, well, is it true for 1? Is it true for 2? Is it true for 3? Is it true? It's like, not necessarily at all, no. Because the law of small numbers is that conjectures that are true for a few of the first numbers are often false later. And then this gets into cases for infinite induction. Infinite induction is the idea of establishing what's so for a case is so for all the numbers that so follow it. Now, is it complete and true? It's like, no, it is, and that the outside and the deductive analysis in the greater universal mathematical objects, there are inductive impasses. So in that sense, then there's things only available to more reflective notions that deductive about the space. That it is true inside that bounded fragment in the theory, but that under reflection, it's not necessarily the thorough and replete. So it's just to be so that otherwise you can find any mathematician, if you give them a proof by induction, they'll have to have a very careful consideration, and it'll be in terms of the objects themselves that there already are, and what properties must have where they live, and maybe and then whether it involves assigning other typical aspects of space, like it's like geometry or it's like numbers, so it has to live in the whole world of them, and this kind of thing. Vis-a-vis, this is just true about every piece of track on this train length. So it's fact that proofs by induction will prove to most people who are naive in proof theory anything. And it is what it is. And there are others. So one might discover theorem 5 that is this C. So it's the root. It's the root of n plus 1 minus the root of n is less than the root of n minus the root of n minus 1. So I can definitely see that, n plus 1 is greater than n, and is greater than n minus 1. These are integers, and they're positive integers, and so then the root of n plus 1 is greater than root of n, and the root is greater than root of n minus 1. And because these inequalities have been built up in the transitivity of a trichotomy in these relations. And then in terms of 1 over root n as being as small as smaller than the difference of the root n and root n minus 1, and greater than the difference of root n plus 1 and root n, is about this notion that the successive differences of roots, integers, successive differences of roots of successive and previous integers, n plus 1 and n, their difference, their roots, and n minus 1, their difference, their roots, that 1 over root n is between them. One might discover theorem 5 by experimenting with the obvious statement that root n plus 1 is greater than root n. Indeed, that is clear. I might have just glanced and found that peripherally, and but subconsciously, I if so, because I would tell you if I read ahead, or otherwise was using information unavailable to both of us. So the following proof is just a successful experiment. Proof: since root of n plus 1 is greater than root n, then he has that root of n plus 1 is plus root n over 2 is greater than 2 over 2 root n over 2. So he's using the fact that of one of these common inequalities, there's got to be 4. That I'm kind of like if A is greater than B, then A plus B is greater than B plus B. So I was thinking about this the other day in terms of defining A and B as positive numbers, and then A greater than 0, and then that if A minus B greater than 0, then A greater than B. And so I got to think about, well, what about a recursive definition where it's like A is greater than B if A plus B is greater than B plus B, and A plus 2B is greater than A plus 3B, and A plus 4B is greater than 5B, and carrying it out in that sense. So then what's established is a schema for a case for infinite induction that A plus Bn is greater than, or A plus B n times n minus 1 is greater than Bn. That kind of formula would serve well here in this case, then, that here he goes on to explain. Therefore, by theorem 3, that he just uses algebra and the identity that it is, the formula, the equation, and just inverts both sides, because here he doesn't have to worry about division by 0, so it's free to do so in these algebraic quantities. So 2 over this quantity, root n plus 1 plus root n, is less than 1 over root n. They canceled the 2 from either side, or divided both sides by 2. So using these rules of this inductive case to then make an example and a template to show a form, it's all about forms. Closed forms, extended forms, infinite forms. The symbols are in their lists, and the relations, the expressions, called forms. And so then this ones are like so. It says now 1 over root n appears on the right, and so then conversely, you just kind of solve it the other way for then establishing this inequality, that this root of n plus 1 minus root n over 2 is greater than, less than, respectively, 1 over root n is less than 2 root n minus 2 root n minus 1. The differences. And it would be kind of so with regards to whether then you want to just make that infinite chain about then the n minus 2 and n minus 3 and n minus 4, and then you'd have that between successively 1 over root n, 1 over root n minus 1, 1 over root n minus 2, dot, dot, dot. That is so established here and is making a case for induction. The base case then is as to whether it's shown that after the base case that the inductive case applies for k and k plus 1, then that it's so for all. And so then you could just write that out infinitely, or take any subsection or bounded region of that. Call that a fact. Call it a form and a relation of equations. Then that equations basically all chain together and make one equation. So in the whole analysis of equations and systems of equations is this. They all equate to the same thing. They are one continuous line, and any one, the first one equals the last one. And so you can interchange them, and they're like so. But then in these systems of these inequalities, that it's a transitive relation, but they're not interchangeable or exchangeable, then you can only write it in terms of that if the intermediate one is removed, then the extreme ones still maintain the same relation, but you can't replace it in the equation with something that is not its greatest lower bound or least upper bound. So in this sense, the notion of the systems of equations and systems of inequalities and what they mean in these forms and how they read and write out is to be considered about how the manipulation and the algebraic expressions that can be arrived at, and the facts and conjectures, but directly proofs then, because the properties is direct and simple cases and statements for induction, that this notion of the inductive inference makes it possible then to treat equalities and inequalities in their relations of systems of equations and systems of inequations as the same, where it's possible that you can always take a middling term to replace a later term, and an exchangeable when possible, when you can't always take a later term to replace a middling term. Then that makes for the derivations of these quantities and so on, about how that ends up becoming things that describe the very fundamental theorems that then are used as general rules to establish triangle inequality and this kind of thing, and about then that reasoning becoming inherent and thus implicit, and thus can be left out of the consideration otherwise, and what would have to be just larger and larger systems of equations or systems of inequalities, that then they can be go back to being treated as algebraic quantities otherwise, because then it will be in terms of these limits and so on. So in this sense, it's just for making for algebra and this trial and error, or the experiment, or trying to put together forms and relations that then can find other forms and relations, how to solve it, or as the polia, and this and that. But as a guy who wrote a book, how to solve it, and all these kind of other ideas that get into the derivational dynamics, what it's called here, derivations, manipulations or derivations, how to make a grab bag toolkit of what are these derivations that apply, and under what conditions and what sections or regions of the derivations they apply, and they can be applied, and they make another section or region of a derivation. That in terms of that being one continuous flow of derivations is a way to look at this kind of in the first class sense, meaning first class meaning of for its own sake and merits, and analyzes its own kind of object. And then that is after those, then there's still others, but then these would reflect and represent what would make it possible then to combinatorially enumerate a set of these things, or a collection of these things, to make it possible to look around at them and see which ones might apply, and then otherwise, if there's a goal, to reach such goal. So that's simple. Since this is the quantity we are trying to estimate, it is natural next to eliminate the square roots in the denominator on the left. Call the entity, and this is x squared plus x squared minus y squared equals x plus y, x minus y. And it's also about x squared minus 1. And it's x squared minus y squared being x plus y, x minus y is a pretty critical thing, because x squared equals x times x. And so when it's about the difference between, like, I think of it like this, like a 6 by 6 square is 36, and a 5 by 7 square is 35. And so by adding to one side and removing to the other side from the square, you always end up with one less, that x squared minus 1 equals x plus y, x minus y. And so this gets into one of these great connections between algebra and geometry in integers, about x squared minus y squared. And so this is just kind of speaking to the fact that it's very, very regular and usual to think of this as an identity, because it's one of those particular ones that holds up for a relation that maintains an integer relation, that by adding 1 to the length of one side of a square and removing 1 from the length of the other side of the square, you end up with a square, or the area of a square, that is 1 less. And so it's a very remarkable thing. And this was discussed a long, long time ago in these talks, is about this x squared plus minus 1. What does that mean? Well, if you add 1 to the area of a square, what does that get you? Is its side length plus 1 or this or that? It's like, well, no, but that's kind of the idea, is that this second scale of numbers, right up about it, about the x squared plus minus 1, about if you think of 36 and then scale that up to 37, just inflate it to where it has area 37, but then you take the sides and divide them into 6, bring that back down, and so you have like 37/36. This is the x squared plus minus 1 bit. And so then for this, well, what would that mean for x squared plus y squared? Well, that's different because that's sum of squares. But what you want to figure out is kind of what that means in terms of the scaling relation that lives about the difference between x squared plus minus 1. That would be essentially a formula relation. And then what it is a kind of thing. And so then that gets into other notions about the products of monomials and polynomials and multinomials. The name, or the nomial, is like how many names of variables is it? There's x and y, so it's a multinomial. It's binomial. And what's but at the same time, sometimes they'll say like x squared plus constants is that. So there's a little confluence of the terms there for the polynomials, binomials, multinomials, monomials. The monomials are the simplest with a variable and a constant, and then there's sums and products. And so that's kind of this area, this x squared plus minus 1 is about a formula. When you take a square that's x squared, you inflate it as to x squared minus plus 1. And then what that means in terms of that, if you were to actually just remove one side by that one length and add to the other one that other length, then it maintains otherwise that ratio that's so amazing that is 35/36. The area in that square that so results. And then the other one is 37/36. That it's not, but then that's related by this other step of the scale to make a side by side of that and show what it would look like when things kind of bracket on down. That, for example, when if you think of a balloon in a square conduit, and that much is how it happens when it happens that it can only increase or decrease by length 1 at a time. So it's digital, it's discrete about, otherwise what would be a continuous transformation between them. And that's thinking, well, not just the differences, but the propensity and tendencies when things come or go from one size to the next in this system of sums and differences. So anyways, that is the kind of thing that goes into the dynamics of such what lives in this very simple aspect of something like x squared, which is great for geometry. And one thing that I wondered about when I later kind of learned about it, that we never learned geometric proofs so much as by like drawing a square and counting the boxes, because we learned algebra, and then the roots were, they lived in the numbers instead of in the geometric shapes, but they do, and so that's a key thing to get figured out. So for where they don't, then it's possible to build up those between them, and that shows that they do. For arithmetizations, algebraizations, and geometrizations. So anyways, we call the identity x plus y, x minus y equals x squared minus y squared, which we specialize to the form root n plus 1 plus root n times quantity root n plus 1 minus root n equals root n plus 1 quantity squared minus root n squared equals n. The right-hand member of the identity is obviously the number 1, hence multiplying the numerator, it's x squared minus 1. And here that is x squared plus 1 when x is 0. So the right-hand member of this identity is obviously the number 1. Hence, multiplying the numerator and denominator of the left-hand member of the last inequality by root n plus 1 minus root n, we find that this quantity 2 over this quantity root n plus 1 plus root n equals 2 times this quantity root n plus 1 minus root n. Statements 1 and 2 together reveal that 2 times this quantity root n plus 1 minus root n equals 1 over root n. So it's established the left hand, or the two left side terms of this 3-term relation in inequality. And then it's to be seen the rest of it, which is one, he says, which is 1/2 of what we want to prove. And so you notice some of the flowery language that he uses to reveal, to demonstrate, to show, and this are from a simpler subset that allows at least some, albeit mathematical, stylistic input that though reflects to only a few such terms that it is so. And then he asks, which of our basic theorems have we used in this proof? Well, pretty much all of them. Yeah. See, he says, now we shall use this to solve this. What is this? 1 over 1 plus 1 over root 2 plus 1 over root 3 plus 1 over 999 plus 1 over 10,000. We shall now use theorem 5 to solve the problem at hand. Let us write down the conclusion of the theorem in the 10,000 particular cases, n equals 1 to 2 to 10,000. In the case of n equals 1, we can afford to replace the right-hand estimate by an equality since the remaining 9999 cases will still involve inequalities. Doing this, we can get a better final estimate. And so he sets up that, and he just writes out for 1 over 10,000 that's between this difference of the roots of the higher number and this difference of the roots of the lower number. To obtain an approximation for the number we are considering, we add the corresponding members of these inequalities to each other one by one and observe that all but the first and last terms in the sum of the left hand appear twice. So he wants to find that the sum is the middle of this table of inequalities. And so then he adds up all the terms in the middle and adds up all the terms on the right and adds up all the terms on the left. And then that the middle is between, the sum of the middle is between the sum of the left and the sum of the right. Whereas if it equals, you could just multiply it. So he's establishing this. That this sum and this equals makes sure these scaling things, looking back to this notion of this scaling powers, about what these inequalities will reflect, that what is a system of equalities can be summed up, that it can be multiplied, and that what is a system of inequalities can be summed up but not multiplied. Well, you can take its average, but it might not. It would not be valid to state that it is so. You'd have to have something as attributing each of the greater than less than after the average. And then that whether that was so would demand its own proof, and its own system of notation, and its own implicits and explicits, and its own carriage in the notation and the symmetry. But it could be a thing. You hear that it's kind of a thing. So, and then sum and the other day adding up each other one by one, observe that all but the last and first terms in the sum of the left-hand members appear twice, one with a plus and one with a minus. And so then he can write a shorter closed form for the sum, because he can write that some of the terms that are duplicated are pairwise in terms duplicated, and then that he can make up a form for those. If we adopt a suitable notation, we can write down the preceding argument more neatly. This notation is called summation notation, and then he writes capital sigma, Greek letter that looks like E, it's like so, sigma, and it's this summation sign, and then it has beneath it in a subscript the index of the summation, a variable name like n or I, and its starting element, that whether it's 0 based or 1 based, usually 1, but whatever is the beginning of these terms, that variable is then reflected for each iteration, that in the subscript of the sigma sign will be the maximum or end index for the start and end index of the variable of summation. Then it follows that the expression contained within has that it represents a sum of those n many terms, each one with the expression any occurrence of the index of summation represented with the value of the index of summation. So, for example, you can imagine an expression where there's no presence of the variable in this expression, and then it's a constant term, and you can just multiply it. That it reflects on when it's a system of inequalities, it's like it's a constant term, the index of summation, so you can just ignore it and multiply it. Linearly scales. And otherwise, then it gets into like the more these terms that go in there, then the more terms that index and live in on the index summation. And then we get into how to make it so that there's considered what would be these differential quantities in and about and around and under these summations and productions or products, capital pi, which looks like two i's together with a bar that connected at the top, for multiplying the expressions together instead of adding the expressions together. That this is a way to consider making for operator calculus to get in and out of these kinds of things. What would be for recurrence relations? What would be for the umbral calculus? Giancarlo Rota, R-O-T-A, he's a guy, and he wrote this thing about the umbral calculus, about finite differences. It's about the calculuses of finite differences, finite or finite differences. I say either finite or finite, kind of accordingly with style or accent, and then say infinite, because very few people say infinite, but many people say finite, but many people and more these days say finite for finite. So he describes and he establishes, and then he puts into the syntax the summation notation. And now anywhere that syntax exists, it can be replaced with its expression that it defines to represent in template. Then and then it's free of anywhere otherwise, like considerations about the derivations and this and that, as long as there aren't interactions with the other constants in the derivations and this and that. So it's a thing, and it's nice to see this author kind of bring it up this way, because then it helps establish that for all sorts of these algebraic quantities, and especially in this world where the identity dimension is a thing, and I want to be able to figure out how to make more of these notions of these derivational quantities be well defined, and also to make it so that when there are implicits and reformulation, and when there are variables that parameterize themselves that make so for these things, the like this is how we steer up the grade and drive up the ridge, keeping it together, that it will be defined in terms of like so. He also illustrates that like sometimes the directly to the right of the summation sign, they'll just have the index of summation k equals 1 to k equals 4, this kind of its placement. And so the mathematical symbols or math formatting, math mode, is linear left to right largely. And so it's not really like a free form way to draw things, because it has to be typeset. And so and that just gets back into the superscript and subscript, and that there's four corners of a symbol, and that there's parentheses and brackets, and back and forth, and more of those. What result writing these things like so. Then when there's notions of diagrams and category theory, well, what's category's greatest contribution? Well, basically they just make four boxes, and then they have arrows between them. And so it starts looking more like a general flow chart or a transition diagram, a state transition diagram. But here it's linear, and that's usually a sensible and fungible notation. but it does expand under these terms, like these iterative terms, addition and multiplication and powers and exponents, or summations and productions of these otherwise as elementary functions, elementary expressions in the syntax of both arithmetic and algebra. Here that our arithmetic and algebra are the same, largely. That this is how it's going, this way. Well, anyways, that's a few more pages in this book about still haven't quite got up to the geometric and arithmetic mean, but we have got up to systems of equations and systems of inequalities, and the notions that when they can be represented in terms of the transitive and equations, and that relation is relation with regards to then the coming together and apart of equations and tautologies, the meeting and parting, the being equal or more same or different, and all these kinds of things, or less than or greater than, or like varying and invarying, and these kinds of complementary concepts and concerns will so follow as a rounder type of descriptive differential dynamics. Well, thanks for joining today. I hope that all is well with you and yours and this fine sunny day, and that it's not like 90 degrees or too hot, you know. It's a thing. Hey, have a great day.